Good afternoon, everyone. I'm not going to tell you about mussels or about anything that live in the sea, but I'm still in a session about valuing biodiversity. And I'm going to report to you about a project that we started with a big group of colleagues, that some of them are listed there as co-author, about how we could come up with an approach to actually map the ecological infrastructure. And you'll see, I'll explain the talk just now, but ecological infrastructure, you can see it as one way to value the importance of biodiversity and highlight it, I guess, in the map. Okay, this is what I'll try to cover this afternoon, quickly in the talk. I'm going to talk about a partnership, another partnership called the uMgeni Ecological Infrastructure Partnership. And I'll give you a bit of a background about what are terms, another new term. Sometimes we're good to create new terms, and this is one of them. Discuss about previous mapping initiatives and challenges in mapping the ecological infrastructure. Tell you a bit more about our approach and share with you some of those results that we've managed to get so far. So this is an ongoing project, and next year hopefully we might be able to present some more detailed results. So this is taking place in the uMgeni catchment. For some of you who are coming from outside the area in KZN, where we are in the uMgeni catchment. So this is the area all around from Durban all the way up to some of the mountain that you see. So that's the area. It might look green, it might look nice, it might have been raining over the last few days, but actually it's a stressed catchment from many different points of view. And there's many ways you can illustrate that. I'm sure I get this point to work. Okay. Oh, okay. I don't know. You'll show me. Anyway, so these are different aspects. There have been a couple of reports in the newspaper that talk about the level of invasion of this catchment. Okay, there we go. Thank you. And this is some recent study that shows the area of decline of natural habitat. So basically the situation is such that the catchment, agriculture, urbanization is taking place, and it resulted in the catchment when you cross the 50 borderline. In other words, we've got less natural habitat and more urban and agriculture area. We put a lot of pressure on the amount of water that we need from this catchment. And this was illustrated recently by the Lions River walk. The Lions River is one of the rivers that we have up there, and when they highlighted actually the condition of the river by walking all the way from the source to the sea. So this led to the need to start to working together, and that's where came this partnership. And that came because simply largely Durban realized when they have a big problem here of water quality and quantity. It doesn't matter if they put a new dam or if they put like new piping infrastructure, whatever infrastructure they put, the growing demand of the population always actually result in not having enough water of good quality or quantity. And that comes largely because of the modification of the catchment in terms of the habitat I've shown. So I think it was last year or 2 years ago they started that to get a big group of stakeholders and 23 different partners involved. This range from NGOs, provincial and national department, the uMgeni Water, which is the water board that deals with the water in this area, a multi-stakeholder involvement that decided to find a new way to deal with the problem, not necessarily making a new dam or a new pipe, and think about what's the role of our natural system, our ecosystem, in actually providing the what is called the ecological infrastructure that will result in good water. So I'll explain that just now. So that for us is seen as a way that we can actually invest in our natural system to provide more water and of better quality. So ecological infrastructure is defined as, and that comes from the work that Zambia have released just recently. It's a framework for investing in ecological infrastructure. It's defined as functioning ecosystem that produce and deliver valuable services to people. So what I mean by that is that this area here, we rely on access to fresh water, be able to regulate climate, limiting soil erosion. These are things that are provided actually that don't just come out of nowhere, and usually the natural system play a big role. For example, your grassland play a big role in the way the water gets infiltrated and to contribute to groundwater, contribute to base flow, so they have a role to play. And often this has been undervalued. And if you want, it's the equivalent of what is built and hard infrastructure, but from the natural side. So that's what ecological infrastructure is about. And it's been seen as maybe a new way to highlight the importance of our natural system. So that's why it relates to the theme of the session today. So this big partnership there of the 23 or so stakeholders is currently implemented for 3 different pilot projects. This is on-the-ground implementation where they try to actually test some of those ideas, and then 3 research projects that work in parallel try to derive the research and the understanding around that so-called infrastructure. And that's what I'm going to explain to you a little bit about today. So we have a project that is actually, it's a research project led by Sandy and uMgeni, and we've got all those objectives there. I think we're quite a bit ambitious in terms of what we wanted to do. And what I will try to do today is to unpack a little bit that first one, which is to develop methods for mapping ecological infrastructure and be able to identify in the catchment where or areas are important to the provision of those services related to water. And then we can, all the way from the identified priority sites, work out intervention that will be required and come up with an investment plan that will result in improvement in water quality and quantity. So this is a long-term objective. The previous mapping initiative that was done recently, actually, this is recent work around mapping the infrastructure, highlighting areas that are important in the catchment. Some of them are shown here. We're actually based largely on the land cover assessment. So what I mean by that is that either through expert knowledge or through information, you can extrapolate and say, well, in general, let's say natural grassland, provide, and you can score there maybe, have a score of 4 for regulating water maybe, and and your forest might have a score of 5, and your agriculture system will have a score of 2. So it's a kind of a scoring exercise based on land cover. And I'm simplifying, but that's largely the logic behind it. Yeah? Some of the challenges that we had, it was difficult to identify the contribution of the broader landscape. What I mean by that is that it's relatively easy to say that a riparian area are important to maintain the quality of our river, and we should have intact riparian area. But what's the role of all those, in the upper catchment of all those mountain area, the more like grassland that we have in the mountain in the upper part of the catchment? The other issue is to quantify the benefit more in terms of water quantity and quality. So can we actually tell us how many extra liters, what's going to be the change in the water quantity that you're going to get, how much water we can extract or we can get from investing in better management of the catchment. So that was some of the challenge. So a whole group of scientists coming from different backgrounds, from ecologists, hydrologists, other disciplines had to come together and say, well, how we could come up with a better approach that will address some of those concerns. Yeah? So I will show you just now, and it's underpinned by a hydrological model. It's called ACRU, that has been a lot in actually being able to quantify all aspects related to water flow regime. The services that we use in our approach, in other words, we're trying to find out where the area and the catchment are important that contribute to flow regime, and some of the examples will be the base flow and dry season. I will explain just that. Attenuation of flood and the ability to prevent damage by flood, and area is also important for maintaining the quality of our water in the river maintaining the quality, and that also includes sediment retention. Yeah, the ability to prevent actually sediment to enter into a river system and clog our dam and clog our infrastructure. So this is what we're trying to do. And those two services actually they work together, because often if you have better flow, you also have better water quality through the dilution effect. So the approach is based again on hydrological model. I will unpack it a little bit later. I try to simplify it because the more I'm not an hydrologist, and the more I try to understand how ACRU works, the more I realize it's actually quite complicated. But it's based on various different aspects that I will explain just now. But in short, it's a process-based model that operates over daily time steps and that gives you as an output some variable with regard to flow. So this is a simplified picture, and the model, if you want to operate a bit like that, it will rain on a given time of the day. The vegetation will intercept, the rain that are fallen, and they need to eventually reach, the topsoil, depending on what you have on the surface layer, whether it's agriculture or whether it's a natural grassland. Eventually reach the subsoil, and then a certain amount will go into base flow, and a certain amount will go into storm flow, and eventually that will reach what you have in your river system. What we're interested here for us, we say how we can improve if you want the surface layer, so that's what we have, whether we have grassland in good condition, whether we have grassland in restored grassland, so that we end up having more base flow. So this is, if you want, the approach that we're trying to get. Yeah. Conceptualize, so this is dividing the catchment into many different units based on the current land cover, what they have at the moment, whether it's forest, grassland, and all this feed through the model, and at the end tell us the impact that they have with regard to the river system. So it's quite a complex model that requires a lot of parameters, and it's an improvement compared to the previous approach because it doesn't just simply rear land cover, but it's a proper hydrological model. The type of output that you get out of that is actually a long spreadsheet full of numbers. And you can map it like that, and it shows you over time what's happened, in that case, that the stream flow, what's happened, what simulates the stream flow. That model has been tested and used in many different examples. It's quite a good model. You can see the dotted line is what is observed, and the black line is what is simulated. So in short, it's a model that can replicate what's happened. So what you can do, you can say based on 30 years of data on climate, knowing the climate for the last 30 years, you can use that model to estimate if you have natural grassland, or if you have degraded grassland, or if you have forest or agriculture, what type of stream flow you're likely to get. Yeah. So our approach has been to use that starting from, and I'll give you an example, this is a bit of a complicated slide, starting from a demand point, let's say Midma, looking at it on the basis of the condition of that area, be able to identify the type of hydrological benefit we can get, the type of flow we can get, and then we can change that and say, well, suddenly if this area gets restored, if this area gets actually converted to agriculture, what are going to be the change and where we're going to get the greatest difference? So we can use this model in a scenario type of analysis to see what's going to be the impact of future land use or restoration on actually our water-related services. So for the uMgeni catchment, to come back to the uMgeni catchment, this map shows the land use in many different colors. What we're interested here is the relative contribution of those green areas, and which one are more important that we need to be considered that to contribute to water-related services. Yeah? And that's what we're going to try to do. To do that, we divide this whole area that we're getting catchment into, you can't see them very well, but 145 little catchment. These are those little lines there that are shown in gray, and that's the unit that the model uses after to operate. So I'm going to try to take you through the approach in a more simple way. We start by looking at, let's say, a particular area that you're concerned, like a dam. You might have drove over that dam over the next few days. Midma Dam is just sitting above there. Yeah. The key services that the dam provides is actually regular water supply. That's what we are interested in. Yeah. The relevant hydrological process that we're concerned is actually making sure that during this dry season, and we had quite a dry season actually this year, we had enough base flow to make sure we don't reach a critical level, of our dam. So we model the hydrology based on the ACRU model, and from there we can use that to identify which grassland area in the upper Midma are important to contribute to that base flow. And that will tell us, therefore, in those areas, we can design the right intervention and probably, let's say, have incentive for not exceeding grazing capacity, that we don't damage our grassland, so that we can have that base flow that we're interested. So this is the whole logic that we're trying to do by combining, therefore, the hydrological process together with kind of the evaluation of the importance of this area. So a quick example about some of the results that we start to have at the moment. We've just zoomed into one section of the catchment. The Lions River is just sitting above us. And the question that we have here is all those green areas you see here, these are the remaining grassland. Which one are most important to contribute to, let's say, base flow? So and then which one, therefore, we could call the ecological infrastructure. Yeah, that's what we're trying to do. So we run that through the model, and the model gives us some numbers. So I was told by the hydrologist that those numbers are not actually absolute. They are primary estimates, so you guys shouldn't pay attention too much to the number, but rather the ranking, I think, is what will be more important. These are all those different subunits, and what you can see is that not all degraded grassland contribute the same to base flow, so the higher the more important, if you want. And we can see that the same for natural vegetation. So the grassland in the Lions River catchment 11, if you want, give you the greatest contribution to base flow. See, those are the one that you want to maintain natural condition. Okay? So you want to avoid development there because you're going to seriously impact on your ecological infrastructure. We can also do that look at those that are degraded, and there's quite a few that are degraded. What are the gain that we'll get if we restore them? So we can again use the model and see what type of gain we're going to get. And I will tell us there where the plus RD means we get a greater gain than where we just have a plus. So this area that I've highlighted now in red there, in catchment 10, 12, and 14, this ecological infrastructure is currently degraded, and should we were to restore it, we'll get a much better, actually, a flow and a much better hydrological system operating the Lions River. So that's the approach that we're trying to do, so that from there we can come back to our map and say, well, actually, in this area, the important area to maintain natural is in that catchment 11, because that model is telling us this is the most important area to contribute to base flow. And then from there we can go on the ground and decide what is feasible, which area we could actually invest in actually maintaining that ecological infrastructure. The model is telling us that the catchment 10, 12, and 14, those ones there, are actually important area to restore. And a little red area that we have this, or degraded grassland, that should we restore them, we get a much greater gain in ecological infrastructure than if we were to restore degraded area elsewhere. So this starts to give us a better indication about to quantify the type of benefit we could get by investing into either maintaining a natural area or actually restoring area that have been degraded. So the next step where we are at in the project at the moment, that we still have to model the entire catchment. I've just shown you what have we done from 6 catchments out of 145. From there we'll be able to identify a priority area within the whole catchment, and then we can move from those priority areas, convert them into look at investment plan, the right type of intervention that should result in the greatest benefit in terms of hydrological regime. So that's what I have to present for you today, and thank you.
Thank you.